Chapter 4 Electricity. Electric charge. When a comb, after combing dry hair, is brought near small pieces of a paper, they get attracted to comb. Similarly, an attractive force results when a glass rod is rubbed with silk and when a plastic rod is rubbed with fur. In this process, the electrical charges that get developed on glass rod and plastic rod are of opposite type. While rubbing these rods, that is during friction, the glass rod acquires positive charges and plastic rod acquires negative charges. Thus, fundamental electric charges are of two types: positive electric charge called proton and negative electric charge called electron. Electric charge, like mass, is an intrinsic property of electron and proton and difficult to define. In SI unit system, charge is measured in coulomb, represented by symbol C. The magnitude of charge on electron and proton is same, but to understand the interactions between them, electric charge of proton is considered positive and that of electron is considered negative. Charge of an electron. E is equal to minus 1.6 into 10 raised to minus 19 coulomb. Charge on proton. E is equal to plus 1.6 into 10 raised to minus 19 coulomb. During the interaction among the electric charges, there is a force of repulsion between two like charges, that is between two electrons and between two protons. There is a force of repulsion, whereas there is a force of attraction between two unlike charges, that is between a proton and an electron. There is a force of attraction. The magnitude of electric force between two electric charges can be calculated by using Coulomb's law given by scientist Coulomb. Electric current. We are familiar with the flow of water. The quantity of water flowing in the river is called water current. Similarly, the amount of charge flowing through the conductor, for example, copper wire, is called electric current. To obtain electric current, flow of electrons is necessary. In atoms, the electrons move around the nucleus, whereas protons remain bounded in the nucleus. In atoms of metals, under normal conditions, the attractive force between the outermost electrons and the protons residing in nucleus is comparatively very small. During the formation of metallic materials, these valence electrons get separated from their parent atoms and move in random motion within the metallic material. Such electrons are called free electrons. Such free electrons are responsible for the conduction of electric current. Metals like copper, silver, and aluminium have plenty of such free electrons. The conduction of electric current can easily take place in such materials, so they are called conductors. The materials like rubber, glass, and plastic do not have free electrons, so the conduction of electric current through them is not possible. So, such materials are called insulators. If external energy is provided to a conductor, then the flow of free electrons present in the conductor can be obtained. Here, a conductor named copper is shown in wire form. Let us think about any one cross-section which is perpendicular to this conducting wire. It contains free electrons moving randomly. In any given interval of time, the number of electrons moving to the right side of cross-section equal to that moving to the left. So, the net quantity of electric charge flowing through cross-section is 0. Therefore, the electric current is not formed even though there is a motion of free electrons in conducting wires. However, if the energy is provided to the conductor through battery, the flow of free electrons can be obtained in conductor from negative terminal to positive terminal of the battery. Thus, the net quantity of charge passing through the cross-section does not remain 0, and the electric current is said to be formed in a conductor. Information about electrons were obtained after experiments performed by J.J. Thomson in 1897 AD. Earlier, scientists believed that the electric current results only due to the motion of positive charges, and the direction of motion of positive charge was considered as the direction of electric current. Even after the discovery of electron, at present, the direction of motion of positive electric charge is taken as direction of conventional electric current. Thus, the direction of conventional electric current is opposite to the direction of flow of electrons. Electric current means rate of flow of electric charges. That means the net quantity of electric charges flowing through any cross-section of conductor is defined as electric current. Thus, electric current is equal to quantity of electric charge upon time. If Q is the amount of electric charge passing through any cross-section of conductor in time t, electric current I is equal to Q upon T. Equation 1. From the above equation 1, we can say that if the quantity of electric charge equal to 1 coulomb is passing through the conductor in 1 second, the electric current of 1 ampere is said to be flowing through the conductor. Unit of electric current is ampere, symbol A, on the name of French scientist André Ampere, who performed many important experiments regarding electric current and designed meters to measure electric current. Electric current is measured in ampere. In SI system, the unit of electric current is equal to coulomb upon second. Smaller units of electric current are milliampere and microampere. 1 milliampere is equal to 10 raised to minus 3 ampere. 1 microampere is equal to 10 raised to minus 6 ampere. The electric current flowing through the conductor is measured by an instrument called ammeter. If the number of electrons passing through the cross-section of conductor in time t equals to N, then the quantity of charge passing through the cross section will be Q is equal to NE. So, the equation of electric current I is equal to Q upon T can be rewritten as I is equal to N into E upon T, where E is equal to 1.6 into 10 raised to minus 19 coulomb is charge of an electron. Electric potential and electric potential difference. Electric potential. We have seen that the flow of electric charge is necessary to obtain an electric current. How can this electric charge be made to flow in a conductor? To understand this, let us understand flow of water. As shown here, first pour more amount of water in vessel A and less amount of water in vessel B. Now connect these vessels through a tube and observe water flowing from vessel A to vessel B. Here, the water pressure is more in vessel A and less in vessel B. Thus, due to pressure difference, water flows from vessel A to vessel B. Similarly, if we can produce the electric potential difference across the ends of a conductor, we can get flow of electrons and hence electric current flowing through conductor. This difference in the electric potential is known as electric potential difference. Before understanding electric potential difference, let us understand electric potential. For the flow of electric charges, work is to be done. To bring an electric charge near to another charge of same type or to carry an electric charge away from another electric charge of opposite type, work is required to be done against the repulsive and attractive forces respectively. This work gets stored in the form of potential energy. When an electric charge is freed, it attains motion. That is, potential energy gets converted into kinetic energy. Work done on electric charge is called as electric potential. Electric potential is defined as the work required to bring the unit positive charge from infinity to any point against the electric force is known as electric potential at that point. Electric potential is equal to potential energy upon electric charge is equal to work done upon electric charge is equal to W upon Q. Electric potential is represented as voltage in the memory of Italian scientist Alessandro Volta. Its symbol is V. Therefore, V is equal to W upon Q is equal to Joule upon Coulomb is equal to Volt. Unit of electric potential is volt, written in symbol as capital V. SI unit of electric potential is Joule per Coulomb. Electric potential difference. In practice, electric potential has no importance, but changes in electric potential are important. Electric potential difference is defined as the electric potential difference between any 2 points A and B in an electric field, means the work done to bring the unit positive charge from point A to point B against the electric force. Electric potential difference V is equal to work to be done upon electric charge Q. Therefore, V is equal to W upon Q. Electric potential difference in general is known as voltage. Its SI unit is joule per coulomb or volt. If the work done to bring 1 coulomb electric charge from one point to other is 1 joule, then the potential difference between these points is called 1 volt. Therefore, 1 volt is equal to 1 joule upon 1 coulomb. The electric potential difference is measured with voltmeter. The voltmeter is always connected in parallel across 2 points about which the potential difference is to be measured. Let us do an activity to understand how electric potential difference is produced from the cell. Activity 1. As shown here, take dilute sulfuric acid solution in a glass beaker. Dip 2 plates, one copper plate and another zinc plate in this solution. Due to chemical reaction taking place between plates and dilute sulfuric acid solution, copper plate gets positively charged and zinc plate gets negatively charged. Negatively charged plate is called cathode, whereas positively charged plate is called anode. Between these 2 plates, an electric potential difference thus gets established. If a small electric bulb is connected to these plates through a conducting wire, it will glow. In this activity, both plates get charged. It is called charging. Charging of plates takes place because of the chemical reactions. So, it can be said that using Volta's simple cell, we have converted chemical energy into electrical energy. Remember, law of conservation of energy. Energy can neither be created nor can be destroyed. It can be transferred from one form to another. Here, negative electrode, cathode, pushes away free electrons of the conductors, and the positive electrode, anode, pulls these free electrons towards it. As per Coulomb's law, between like charges, there is a repulsive force, and between unlike charges, there is an attractive force. This way, electrons start flowing towards positive terminal from negative terminal, but as you have studied earlier, direction of conventional electric current is opposite to the actual direction of flow of electrons in the conductor. That is from positive terminal to negative terminal outside a cell. We can thus say that an electric potential difference can be created between the 2 terminals of a cell and electric current can be obtained in the circuit. The electric potential at positive terminal of car battery is V1 is equal to plus 12 volt. Whereas the electric potential at negative terminal is V2 is equal to 0 volt. Therefore, the electric potential difference between positive and negative terminals of car battery is delta V is equal to V1 minus V2 is equal to 12 minus 0. is equal to 12 volt. Taking inspiration from Volta's cell, British scientist Humphrey Davy connected many such cells in series and obtained very large voltage. He connected negative terminal of first cell with the positive of second cell, whose negative terminal is connected with positive of third cell, and so on. This way, he connected 2000 cells together in 1808. When two or more cells are connected in series, it is called battery. Total voltage V of all cells connected in series is equal to the algebraic sum of voltages of each cell. If we connect three cells having voltages V1, V2 and V3 each, then total voltage V is equal to V1 plus V2 plus V3. Large voltage so created were very much helpful to scientists for experimental research. In modern era also, for development, electricity is an important form of energy. Electric circuits and symbols. When electrical components such as battery, key, bulb, etc. are connected through a conducting wire, then such an arrangement is called electric circuit. Due to the formation of closed loop circuit, electric current flows through circuit and the bulb glows. Here, an electric circuit is shown with electrical components represented in their respective symbols. Table containing some useful symbols for electric circuit is given here. Ohm's law. Ohm's law has central importance in the study of electricity. German scientist Georg Ohm established the relation between the voltage V and the current I flowing through the circuit. Let us do an activity to understand this relation. Electric circuit to understand Ohm's law. For this activity, take 0.5 meter long nichrome wire, 4 to 5 batteries of 1.5 volt, voltmeter, ammeter and key. As shown in figure, first connect nichrome wire, an alloy of nickel, chromium, manganese and iron, with 1.5 volt battery and ammeter. Now connect the voltmeter between its two ends. it is easy to take observations using these meters. Look at the pointer and scale of this meter. It resembles speedometer of motorcycle. An arrow is shown on battery. It means that voltage of this battery can be changed. Such battery is called variable battery. Instead of a resistor, a small bulb can also be connected. Now press the key on and adjust the battery such that the voltmeter shows 1 volt. Simultaneously, read ammeter and note their value. Repeat this for other voltages in voltmeter as 2 volt, 3 volt, 4 volt and 5 volt. During this experiment, keep key closed while taking observations. After taking all observations, calculate the ratio of V and I and plot V to I graph on graph paper. Take voltage on x-axis and the current on y-axis and plot points on graph corresponding to all values of V and I. On joining all these points, we get a straight line passing through the origin. We can infer from this activity that on increasing voltage, electric current increases proportionately. Graph is a straight line passing from origin, and the ratio of V and I remains constant for different values of voltages. From this experiment, Ohm deduced the relation between electric current I and voltage V, which is known as Ohm's law. Ohm's law. In the definite physical situation, the electric current flowing through the conductor is directly proportional to the potential difference applied across it. I is proportional to V. It is also written as V is proportional to I. Therefore, V is equal to IR, where the proportionality constant R represents the resistance of the circuit. From above equation, resistance R is equal to voltage V upon electric current I. The SI unit of resistance is volt per ampere, which is known as ohm. Its symbol is omega. Therefore, 1 ohm is equal to 1 volt upon 1 ampere. When 1 volt potential difference is applied across the conductor and 1 ampere current flows through it, then resistance of the conductor is said to be 1 ohm. This symbol is used to represent the resistance in the electrical circuits. The resistance of substance depends upon the kind of substance and its physical conditions. For example, temperature. In metallic substance, the resistance increases with the increase in temperature. In a conductor, the free electrons collide with the positive ions during their motion, so that their motion gets opposed. Thus, the motion of electrons means the electric current gets opposed during their motion in a conductor, which is called resistance of conductor. The metallic substance such as copper, aluminium have less resistance. Therefore, we use the copper wire as a conducting wire. The resistance of insulators is very large. The alloys like nichrome are used to make resistive wires. The resistors used in electronic instruments like TV, radio, etc. are made from the mixture of carbon and graphite.